for the antiproton.
Next speaker is Dr. Chen, who is going to tell us about the Nucleon axial form factor. So Chen, please, can you share your screen with us? Are you trying, Chen?
Yeah, it's okay. Share my screen. Yes. Yeah. Can you see it?
Yeah.
Okay, I will begin. Can you see it?
Perfect.
Okay.
Go ahead, please.
Okay. Hello, everyone. It's my pleasure to give a talk in this afternoon. The title of my talk is Form Factors of the Nucleon, Axial, and Pseudoscalar currents. Let's start with the lumped parallel QCD. We know that the hadrons at the bound states are dominated by lumped QCD dynamics. It has two emergent phenomena. The first one is confinement, which means the colored particles have never been seen isolated. It can explain how quarks and gluons bind together. The second one is dynamical chiral symmetry breaking, which means the hadrons do not follow the chiral symmetry pattern. It can explain the most important mass generation mechanism for visible matter in the universe. Neither of these phenomena is apparent in QCD's Lagrangian. However, they play a dominant role in determining the characteristics of real-world QCD. From a quantum field theory point of view, these emergent phenomena could be associated with dramatic dynamically driven changes in the analytic structure of QCD's swing functions, which include the propagators and the vortices. The swing functions are the solutions of the quantum equations of motion, the Dyson swing equations. From my point of view, the most important Dyson swing equation is the gap equation of the dressed quark propagator. Here is the Feynman diagrams of the gap equation. On the left-hand side is the inverse of the fully dressed quark propagator. On the right-hand side, here is a straight line is the inverse of the bare quark propagator plus self-energy. We also know that hadrons are bound states, and so in order to study them, we need the quantum bound state equations. For mesons, we need a two-body bound state equation, the Dyson swing equation. For baryons, we need a three-body bound state equation, the Faddeev equation. Here is the Feynman diagrams of Faddeev equation. These orange half cycles are the baryons Faddeev amplitude. This blue triangle is the three-body irreducible interaction kernel, and these blue boxes are the two-body irreducible scattering kernel. But however, this three-body equation, Faddeev equation, is very complicated. Usually, we use a simplified two-body quark-diquark Faddeev equation. Here is the Feynman diagram of the two-body quark-diquark Faddeev equation. Sorry, I need to close the window. Okay, this blue half cycle here and here is the baryons quark-diquark Faddeev amplitude, and these orange half cycles are the diquark inside the baryons, the diquark's feather spread amplitude. These straight lines are the quark propagators, and this double line is the diquark propagator. So the question is how to solve this two-body quark-diquark Faddeev equation. In principle, we need to solve the gap equation of the dressed quark propagators. We need to solve the Bethe-Sweat equation of the diquark amplitudes. We also need to solve the Dyson equations of the diquark propagators. When we got all the numerical results, we put these numerical results into the right-hand side here, here, and here. Finally, we can get the Faddeev amplitudes in this blue side. However, in this ab initio method is very complicated and has many limits. Or we can construct a QCD kindred model. We can reconstruct the models of the just quark provocators. We construct the models of the dipole amplitudes. We can also construct the dipole provocators. We have put these models to here. We can also get the lattice amplitudes. We have many methods to construct this QCD kindred model. In fact, we have a very successful model. I'm not going to say many details about it. I just want to point out the only adjustable parameters of this model is the dipole masses. We choose the dipole masses to get a good description of the diverse dynamical properties of the nucleon, delta baryon, and the rope resonance. In my point of view, the biggest success of this model is the solution of the 15-year puzzle, the loop resonance. Loop was discovered in 1963. It appears to be an exact copy of the proton, except that its mass is 50% greater and it is unstable. In this paper, Jorge Segovia and his collaborators computed the transition form factors between the nucleon and the loop. And finally, they found that loop is the first radio excitation of the nucleon. Okay, let's turn to form factors. Why are we interested in form factors? Because it contains important information about the structure and the properties of hadrons. We know that different probes correspond to different form factors. For example, the nucleon electromagnetic current it is described by the electromagnetic form factors. In this expression, the F1 is the direct form factor and the F2 is the Pauli form factor. For these form factors, we have a large number of experimental measurements with high precision and up to large momentum transfer. We also have the nucleon axial vector current. It is described by axial vector form factors. In this expression, it has two axial vector form factors, GA and GP. For these form factors, the measurements are much more difficult since they are related to weak processes. GA is the axial form factor. Its experimental data are rather sparse and with large uncertainties. We can see it later. And GP, the induced pseudoscalar form factor, which has only 4 empirical results. I will show you later also. We also have the nucleon pseudoscalar current. It is described by just one form factor, the pseudoscalar form factor. In G5, in this expression, should we point out here that these 3 form factors, GA, GP, and G5, are not independent. They are related by the partial conservation of the axial current relation, the PCLC relation. In this form, any sensible computation of these form factors should satisfy this relation precisely. Now, the question is how to compute form factors. In the quark-dipole framework, the associated symmetry preserved current can be expressed in these 6 diagrams. Diagram 1 means the probes interact with the quark inside the baryon, and the probe 2, diagram 2, the probe interacts with the diquark. Diagram 3 means the probe induces the transition between the scalar and the pseudo-axial vector diquarks inside the baryons. Diagram 4 means the probe interacts with the exchanged quark between 2 diquarks. Diagram 5 means the probe interacts with the diquark's better splitting amplitude. This term is called the Seagull term. And the diagram 6 is a charge conjugation of the Seagull terms. By solving the successful Vadiffer equation successfully, we have had the Vadiffer amplitude psi. We also have the model of the quark propagator and diquark propagators. Now, so it is clear to see that in order to complete this computation, we also need the current quark vertex. We need the current diquark vertex, the current diquark transition vertex. We also need the diquark, the singletons expressions. For the electromagnetic form factors in the Dyson string equation framework, we have a large number of publications, which from last century to last year. These black papers are computed in the quark diquark framework, and these purple papers are computed in the 3-quark framework. However, for the actual form factors, the situation is much poorer. Let's see. The first one was published in last century, and after 3 years, we have another 2 papers. These 3 papers were all computed in the quark diquark framework and also computed in the chiral limit. After 12 years, Guy Ashman and Christian Fischer, they computed this Nucleon's actual form factors in a 3-body framework. In this paper, in the paper with its introduction here, they also point out that the difficulty of the computation of these form factors in the quark diquark framework. Let's see. There are several conceptual issues that complicate the treatment of form factors in the quark diquark framework. The quark diquark model. First, the requirement of current conservation induced the appearance of the Siegel terms. Such terms have been taken into account for the electromagnetic form factors, but their implementation in this case of actual form factors have not yet been possible for technical reasons. Second, to comply with the chiral water identities, a current conservation quark diquark model requires a vector diquarks. In addition to the usual scalar and actual diquarks, such an elaborate treatment of the quark diquark model has not yet been performed. I need to point out that for this reference 50 is this paper, the argument was based on the NGL model. In NGL model, the amplitudes of baryons and diquarks are all constant. In the electromagnetic case, there are some cancellations between these terms. So even in the NGL model, the electromagnetic form factors in the quark diquark model are conserved. However, for the actual vector case, there's no such cancellation. So this is the reason to introduce an artificial vector diquark. However, we found that if we work in a realistic model, we do not need to introduce a vector diquark. The only problem is how to get the expression of this Siegel diagrams. Last year, Christian Fischer, Craig Roberts, Jorge Segovia, and I, we finally solved this problem. We find the solution of the Siegel terms. We also construct the quark vertex and the diquark vertices, and we computed the actual form factors in the quark diquark framework. And this work was published in Physics Letters B in this paper. Besides, we also have a longer paper which include all the technical details. This longer paper was submitted to Physics Review D. Okay, I will show you our numerical results for in the quark diquark framework, and also compare our results to the experimental and the lattice results. Let's begin with the GA, the actual form factor. In these 2 panels, this blue curve with its blue band is our computed GA with its uncertainty. In the upper panel, we compared our results with the different experimental results. As I said before, for GA, its experimental results are sparse and with large uncertainties. Here we made our prediction. We find that our computer results agree with the results of the neutrino proton scattering. And in the lower panel, these green diamonds are the lattice results of Young from Los Alamos, as these blue triangles are the Alessandro's lattice results. We find that in our computer results are in good agreement with the lattice results. And much more, in fact, if we calculate it in detail, we are much more closer to the Young's results. For GP, the induced pseudoscalar form factor, for which we can define the nucleon's induced pseudoscalar charge, GP star, in this expression. For GP, there is another approximation, the pineapple dominance approximation, the PPD relation. It can be expressed in this form. This relation is not an exact relation, but people find that it is very useful. Here, in this panel, this blue dashed line is our directly computed GP, and this long golden dashed line is the PPD results obtained from this expression. We find that our computed results is almost indistinguishable from the PPD results. And in this panel, these three purple cycles are the experimental results. As I said before, for GP up to now, people only have 4 experimental results. These 3 dots plus this GP star. We can find out our results is also a good agreement with the experimental results. And I also give you the lattice results. These brown triangles are the lattice results from Alessandro's groups, and these green diamonds are Young's lattice results from Los Alamos. It's clear to see that our computer results are agree with the Young's lattice results, but obvious larger in a small momentum, larger than Alessandro's results. Here is our computer GP star, and also compare to the experimental and the lattice results. And this blue star is our computer results, and this purple star cycle is the experimental results. Here are the lattice results from different lattice groups. These golden and the gray bands are the theoretical average values from 2 different methods. We can see that our computer results agree with the experimental and these 3 lattice results. And just like this GP is obvious larger than the Alessandro's lattice result. Okay, for GP star, the pseudoscalar form factor. For this form factor, people do not have the experimental results, but we now have some lattice results. In these 2 panels, this blue solid line is our computer results, and in the upper panel, these green diamonds are the lattice results from Young's groups, and in the lower panel, this results is biased lattice results computed from 2 different methods. We can see that in these 2 panels, our computer results is in good agreement with the lattice results. And here,
you have 5 minutes left.
Okay, thank you. And in here, we compare this factor times G5 because we want to animate the influence of the difference of MQ, the Coulomb quark mass, and this nucleon's mass. At the pi mass pole, the residue of G5 is the pi nucleon coupling constant, the G pi n. First, one can define a pion nucleon form factor with capital G pi n. In this expression, this is the capital G pi n. At the pi mass pole, here mq square equals to minus the m pi square. This here is the definition of this pi nucleon coupling constant G pi n. From this expression, we can immediately get the Goldberger-Treiman relation. At q square equals to 0, this GA should equals to G pi n times f pi over mn. We can also define the Goldberger-Treiman discrepancy delta GT in this expression. If we are working in a chiral limit, the mass of the pion should precisely equal to 0. So this delta GT should precisely equal to 0. So we say that this delta GT measures the distance from the chiral limit. In the upper panel is our computed G pi nn times the normalization factor. Here is the blue star is our computer results. The purple cycle, the experimental results, and this Carrier crosses are the lattice results from body computed from two different methods. We can see that our computer results are agree with the lattice results, experimental results, and these lattice results, but here smaller than another lattice results. And in the lower panel, we compare our computed delta GT with the Goldberger-Treiman discrepancy. We compare our computer results, this blue star, with the experimental purple cycle and the Carrier crosses. We find that our computer results is a little larger than the experimental results, but agree with two different lattice results. Okay, finally PCLC. As I said before, any sensible computation should satisfy this PCLC relation precisely, from which we can define the PCLC ratio, RPCLC in this form. If this PCLC relation can be satisfied, so this PCLC ratio should precisely equal to 1. In this panel, we show our directly computed PCLC ratio. This back solid curve is our directly computed results. These oscillations are due to numerical precision. We can see that our computed RPCLC is almost equal to 1 within 0.5%. So it is safely to claim that we prove the PCLC ratio in our framework numerically. On the other hand, in our longer paper, we also give an analytical proof of the PCLC. We take into account of the 6 contributions from 6 quark-dipole equivalence diagrams from diagram 1 to diagram 6. We add them together. Finally, we can find out in our framework, this PCLC relation can be satisfied automatically. So we claim that in our work, we prove the PCLC relation numerically and analytically. And should point out that here, in our construction, we didn't implement the PCLC anywhere. What we implement is just the actual vector water Takahashi identity. We find out if we implement the water Takahashi identity, it can lead to the PCLC relation automatically. Summary. We solved the Singleton problems for the actual and the pseudoscalar currents, which has defined our understanding for more than 20 years. Then we computed the form factors of GA, GP, and G5 successfully. The PCLC relation can be satisfied precisely. Our next step, first, compute the actual delta, equal to delta, equal to Roper, actual form factors. Also, in the three-body framework, we want to revisit the computation of Ashman and Fisher first. Then, what we can see, what can we do next? Thank you.
Thank you very much. Chen. I think that Victor is impatient to ask something. Victor, please.
Thank you very much for a very interesting talk. My question is, you have prediction for pi and nucleon form factor, J, pi, and N.
Yeah.
How your prediction as a function of Q square, you show it here, consistent with phenomenological parameterization used for description of pi and nucleon scattering? And my second question, you mentioned die-quark mass. You are using the die-quark mass as the pole on real energy axis in approximation of rainbow ladder truncation, or it is something else? What is your die-quark mass?
My die-quark mass. Can you repeat your first question?
Well, I have two questions. First, about pi and NN vertex function. And my second question, you mentioned that die-quark mass is parameter in your approach.
Yeah.
Up to my knowledge, actually, die-quark has no certain mass in full DSE. This is artifact of rainbow ladder truncation. Therefore, how you compute the Fadeev amplitude for ground nucleon state? Is it in rainbow ladder approximation or in other approximation?
The first question, we just show this pseudoscalar form factor. We didn't have we didn't do that. We can do that. The result of the G pi N evolve from Q square. The second question, the die-quark function, we didn't work in the RAM ladder. What we did is use a model or a QCD kindred framework. In this model, the die-quark masses are parameters. They are not computed. This is we can put the die-quark masses in our model and finally to solve this Fadeev equation. They are not computed.
Okay. Are there any more questions? Comments? I see no more raised hands. Okay, it seems that everything's clear to everybody. So thank you again, Chen.
Okay, thank you.
Nice overview.